All right, good morning, those of you who are in cyberspace. Uh, I mentioned on Monday, we're gonna actually start a new section today on triple bonds. Hopefully we can get through it. Little resistance, but as always, we need resistance. Okay. Let's see. I'm just waiting for this plugin to install and then we'll get started. Same plugin I've installed every day, 3 days a week since the beginning of the month. I will never understand that. It's coming. All right, there we go. Okay. All right, I want to start out, I think I sent you all a while back. When we first started Alkynes, I think I also introduced you to Alkynes with the triple bonds. So I guess today what I want to do is just a basic overview of the reactions that we're going to study. The two most difficult ones we're going to do first, but they're going to be familiar to you because they follow similar principles as the reactions of alkenes. So I want to, so for reactions of alkynes, I want to first talk about, and again, it's just an overview. The first two reactions we're going to look at mirror hydroboration oxidation from alkenes, and this is not oxymercuration, but it's just mercury catalyzed addition of water, right? But it's the same idea of adding H and OH across the double bond, same idea. All right, so we're going to talk about that. One of the things with alkynes, which are triple bonds, is that they tend to rearrange when you convert them into alcohol. So that's the only trap right here, but we're going to talk about that in a minute. Then we're going to talk about alkyne oxidation, which is very similar to ozonolysis. It's the same type of reaction. That's similar to ozonolysis. Just like the alcohol synthesis is similar to hydroboration or oxymercuration. And then we're going to talk about reduction. Reduction meaning adding H2. You can reduce it all the way down to nothing, or you can reduce it selectively to an alkene, either a cis alkene or a trans alkene, depending on which reagents you use. Right, so I have a mnemonic to help you remember which catalyst does what. So the LCAT, little children always tripping, right? The LC is for Lindlar's. That's the catalyst right there, Lindlar's catalyst. Lindlar's is cis, and then ammonia, which is the next D under the letter D. Ammonia and lithium, so ammonia is trans. So Lindlar's is cis, ammonia is trans. That's just to help you remember when you see the reagents, what the outcome is. So we're going to come back to these and talk about them in more detail. And then, of course, you can reduce it down to nothing if you just use hydrogen gas and palladium on carbon or platinum oxide. The last part of the alkyne puzzle is here, right? Because that alkyne proton has a low peak, well, relatively low pKa. It's not really low. It's not a good acid at all, but with a strong base, you can actually remove it. So you can take that proton which is called the acetylene or acetylenic proton, and pull it off with a strong base. And then from there, you can take that acetylide anion and use it as a nucleophile or a base. Right, you can use it as a nucleophile or a base, depending on the structure of what you're reacting it with. So that's what this part down here is dealing with. If it's primary carbon, which is right here, then it's just going to do substitution. It'll be a nucleophile. If it's a secondary carbon or tertiary carbon, which is what you see right here, it's going to do elimination. Right, so we're going to come back and talk about that in more detail as well, because we've already talked about substitution as well as elimination. So this is not new. All right. Questions? Any questions so far? I want to go back to these reactions right here, because I want to talk about that tautomerism that happens. Right. So let me ask this question. Very generic question. If you saw this reaction with these reagents, what's the first thing you would think of? BH3, I don't have the THF solvent, but it's in THF, followed by hydrogen peroxide. What's the first thing that comes to your mind? Let me turn my volume up in case I miss somebody.
Hydroboration.
Hydroboration followed by oxidation, is that right? Which does what? Tell me the characteristics of that reaction. We know it's anti-Markovnikov. What is it? What's the outcome and what does it do?
It makes an alcohol.
Say that one more time.
It makes an alcohol.
From if you started with an alkene, it would be a alkene to alcohol. But we're starting with triple bond, but you're going to get the same thing. You're going to add H and OH to that triple bond. That's the essence of the reaction. Even if you don't know the mechanism and all the arrows and all the intermediates, you at least know that I'm going to add H to one side and OH to the other side. Now the question is, since it's hydroboration, which goes where? That's the key to understanding the reaction, right? Which is going to go where? Like if the OH, is it going to the most or least substituted side? What's the regiochemistry? You can answer too if you choose. It's anti-Markovnikov. So where's the OH going in this triple bond? Is it going here or here? That's the question, right? Shouldn't the OH go here? Is that right? Because it's anti-Markovnikov. Right, so if we look right here, you can see that this is the outcome. If I do hydroboration on a triple bond, one of the pi bonds gets used up, which you expect. So I have a double bond left, and on one side of that double bond, I've added H. The other side, I've added OH. Y'all following? Anybody not see that? The problem with doing this reaction on triple bonds is that those alcohols are not stable. That's why it's called the enol form. This is unstable. And it's going to rearrange. All right, that's going to rearrange to something else. That's what the other form of the product is on the other side. It's called the keto form. Even though it's an aldehyde, the idea is that it turns into a carbonyl. right? So this for hydroboration oxidation and for the mercury catalyzed process, they both will give you an enol, which will rearrange. That's the hardest part of understanding this. All right? So the way the rearrangement happens, I have it in this box down here. You can see that the OH right here, there's a proton transfer that happens between that OH group and this carbon in the pi bond. Do y'all see that? That's why that pair of electrons is coming from that pi bond to attack that hydrogen. And you can see on the other side, that hydrogen is here. And then at the same time, this pair of electrons is coming, being given back to oxygen, and then you got a pair forming a pi bond. And now you have a pi bond right here. That's how that is called, what we call tautomerism. Keto, enol, tautomerism. If you read that in the chapter, that's what it's going to call it. Keto, enol, tautomerism. Keto, enol, tautomerism. Anytime you make an enol from an alkyne, it's going to tautomerize into a carbonyl, which is a more stable product. So that's why you can't really convert alkynes into alcohols. But once you convert it to the keto form, you can reduce that carbonyl down to an alcohol if that's what you want. But it'll just take an extra step. All right, questions about that? Any questions from anybody online or in person? I didn't want to say the one person in person, but technically we're still hybrid. Any questions? All right, so if you look at the next reaction, you can expect the same thing, right? You got mercury sulfate. It's going to follow the same regiochemistry as oxymercuration. Go ahead. Was that a question or did somebody just come off mute? No. It's going to follow the same regiochemistry. As oxymercuration. Same regiochemistry. So that means it's Markovnikov regiochemistry. That means we add H and OH across the double bond. OH is going to go to the more substituted side of that. I said double bond, I meant triple bond. It's going to go to the more substituted side. Right, and as you can see, this side is more substituted than that side, and that's where my OH ends up. All right, so again, once you get to the enol form, it's going to tautomerize. So let me redraw this. How does that work? How would this tautomerize to give you this? Right, because that's what you get. Is that right? Again, it's all in these three atoms right here. Here, here, and here. Well, four atoms. And the proton is an atom too. So which carbon in that double bond is going to attack that proton? Let's start there. Uh-oh. Would it be the more substituted carbon or the least substituted carbon that's gonna attack the proton? Right, and let's think about this in these terms. So this is. And also think about it like this. Right? Well, if I just shift the double bond over. This is what I would give. So that's how you know where to, where to attack. So these electrons are coming here, right? Like that. These are coming here onto oxygen, and then a pair coming here. All right, so it's those same. Okay. With those same three arrows. So if you're confused about the enol, you can always draw it like the rest. You can draw the resonance form of it, and then work from there. All right, questions about anything? Any questions? All right, let's go to the other half of this worksheet or other quadrant and talk about this oxidation and reduction, because both of these are important processes. If you look at the potassium permanganate reaction, this is potassium permanganate is what we call a superoxidant, so it will oxidize the crap out of anything. And if you get it on you, you gotta live with it for quite some time. They use it for stains when you're doing like thin layer chromatography, and it's purple. And I remember as a grad student, I ruined a brand new pair of Air Max with potassium permanganate. I dropped some on the toe, and that was it. They became work shoes after that. But it's a very, very deep purple dye, and if you get it on your skin, it takes a very long time to get off. And there's nothing you can do to wash it off. It just has to wear out. But anyway, just like ozonolysis, right, what this reaction does in essence, we're not going to go through this mechanism, but what it does in essence is crack that triple bond in half. And each carbon in the triple bond, so there's a carbon here and a carbon here, each carbon in that triple bond becomes a carboxylic acid. In ozonolysis, it just became a ketone or aldehyde, but this is a much stronger oxidant. And so it'll oxidize that carbon, that carbon all the way up to the carboxylic acid. Right? Again, let me go back, because I was preaching this to my, literally preaching it to my 9 o'clock class. If you still have trouble with functional groups, you still have trouble with nucleophiles, electrophiles, acids, bases, it's very important to get that clear, like now, before you go to part 2. Because you're just going to see the same stuff, but on a different level. So your functional groups, if you made flashcards for those, I continue to review those, because when you do reactions, if you don't know what the functional groups are, you're not gonna know what the heck is going on with the reaction, period. All right, so please continue to review your functional groups, and hopefully you made flashcards for your reactions so you can review those as well. All right, so it's similar to ozonolysis. Just crack that triple bond in half. Both carbons in there get oxidized up to acids. All right, any questions? You got a question? All right, let's go down here to reduction. This is oxidation. And let me give you that definition too, because I don't think we touched it. It's weird because I taught the same thing this morning. But in GChem, when you learn oxidation and reduction, when you learn oxidation and reduction, what did it mean to you? If you were taking me for general chemistry and I said something got oxidized, what would that mean to you? Did y'all cover redox? I know y'all covered it. And Biswas and Reeves, depending on who you took it. Right? Oxidation in GChem deals with losing electrons. Is that right? Loss of electrons, increase in charge. And then reduction is the opposite. You gain electrons and you reduce the charge. Right? In organic, it's a little bit different. Oxidation is increasing the number of bonds to oxygen. Or decreasing the number of bonds to hydrogen. That's what that word oxidation means for an organic chemical. Right here. Increase the number of bonds. Get your hand right here. Oxygen or decreasing number of bonds to hydrogen. Right. So when you hear that term oxidation in terms of organic, that's what it means. Normally, it's typically taking a carbon and either converting it to alcohol or converting it to a carbonyl or something like that. Right? The other term reduction is the exact opposite. You either decrease the number of bonds to oxygen, or you increase the number of bonds to hydrogen. That's what reduction means. Decrease the number of bonds to oxygen, increase the number of bonds to hydrogen. So these two reactions are both reductions because they're going to add hydrogens to the triple bond. They're going to add a hydrogen to each side in the triple bond. The thing about organic is that you want your tools that you use in organic to be specific or selective. That's the word we use instead of specific. So if you want to take that triple bond and turn it into a cis alkene, which does matter, because certain reactions that you do on alkenes, if the alkene is trans, it won't work. So if you want a cis alkene, then we have a specific tool that's selective for hydrogenation. Because that's what this is. It's a hydrogenation, but it is a selective hydrogenation. And that's Lindlar's catalyst. All right, so Lindlar's catalyst will take any triple bond and turn it into a cis alkene. You see that? Why is that alkene cis? Did we talk about that, cis and trans? I think I sent y'all a video about that, right? What does cis mean and what does trans mean? You don't have to. I think you know it. Or you can't answer. It's up to you. Look at the two groups on the alkene and their orientation to one another. If it's cis, that means that they're on the same side of one another. The same side of the double bond. If it's trans, that means they're on opposite sides of the double bond. Can you see that? How they're oriented around that double bond? We did talk about that. Because we did nomenclature with cis and trans. At the very beginning of this section. All right, so Lindlar's catalyst, it's a calcium calcium catalyst, if I'm not mistaken. And if you use that with a triple bond, you get a cis alkene. If you want a trans alkene, which matters, right? Trans alkenes are very important, just as cis alkenes are. Right? You use lithium and ammonia. Right? This is more than likely a radical process. That's why it's trans, because the bonds have time to rotate, things like that. So this is likely a radical process or one electron process. But the outcome is to take the alkyne triple bond and convert it into an alkene with trans stereochemistry. Anybody remember what that term means? Stereochemistry? I think I talked about that too when we started talking about cis and trans. Somebody help me out of the 20 or so participants in the participant box. What does stereochemistry mean? Anybody but a dead body. No takers. It's the 3D orientation of a molecule. And so cis and trans are terms used to describe stereochemistry. All right, and again, you can nuke this, right? These are non-selective. This hydrogen with palladium on carbon as the catalyst is a non-selective process. So you can nuke it, and it'll take the triple bond all the way down to an alkane. It will just keep reducing it until there are no pi bonds left. Right? Questions about the reduction? All right. Let's go back to the acetylide formation part. And then we're going to talk about these two, the substitution and elimination reactions, and then we're going to start working through some examples of these reactions. All right, and again, I have a mnemonic in here, 1 sausage, 2 or 3 eggs. So 1, if it's primary, it's a substitution. If it's secondary or tertiary, it's an elimination. Right? That's what triple bond, well, that's what the acetylide anion does, depending on the nature of the substrate that it's interacting with. So if I have a base, let's say KOH, right? That base can come in and pull off this proton. And I want to stress this, even though you see that triple bond drawn like it's drawn, there is a carbon right here. This is a carbon, and so is that. Right, so a lot of people miss that, and they forget that at the end of that triple bond there's a carbon, but there's a carbon there. Right? So I can pull that off. This is acid-base chemistry. What is the acetylide anion if the triple bond is the acid? What's the acetylide anion on the other side? What do we call that? If the acetylide or the triple bond or acetylene on the reactant side is the acid, and I do proton transfer with the acid and pull off the proton and leave it with a negative charge, what's the acetylide anion? What's the proper name for that? Is it the base or is it the conjugate base? It's the conjugate base, is that right? Right, so the acetylide anion is the conjugate base of acetylene, right? So we've seen this before. This is just acid-base chemistry, pKa, acid-base, conjugate acid, conjugate base, so on and so forth. So this is the conjugate base. Right? But it can be a base or a nucleophile, depending on, again, what it's reacting with. So if I react that ion with a simple alkyl halide, it's just gonna do substitution if it's primary. Right, this is actually methyl, so this is, methyl bromide, so it's a step below primary. The primary will have one bond to carbon. So but it's the same, it'll react the same way here. Right, so this is just gonna attack that carbon and kick out bromine as a leaving group. So it'll be this, but back to back, I don't know what it is. Right. What type of substitution is that? Oops, never mind. SN2. Is that right? Now, if your substrate is secondary or tertiary, like we have up here, right? This is a secondary alkyl halide. That carbon right there is secondary. Right? That won't be direct attack. It'll do elimination. Right? E2 elimination. So the acetylide is acting as a base. Right? So one sausage, primary substitution, 2 or 3 eggs, secondary, tertiary elimination. Right, so this is coming here like this, boom. This is coming here. And that's going there. Right, it's an E2 elimination. Which we've seen, right? What would happen? It's a good question. Let's see what you know about E2. What would happen to that elimination? Well, first of all, let me back up. What's the rate law for E2? I think I just made Cameron mad. What's the rate law for E2? Anybody? Look back in your notes if you have to, but that's a question you should be able to answer. It's second order, right? Mm-hmm. A times the concentration of the substrate times the concentration of the base. We've seen this before. What would happen if I triple the concentration of the acetylide anion? What would happen to the rate? The rate would triple. Good. Well, and the same if I triple the concentration of the alkyl halide, which is here. The rate would also triple. Are y'all following that? Anybody not see it? All right. So with the acetylide anion, you can do substitution or elimination. Ooh, that's so tiny. Depending on what the substrate is. If it's a primary alkyl halide, it's going to do substitution. If it's a secondary or tertiary alkyl halide, is going to do elimination. All right, we got 10 minutes and we got a bunch of reactions to do. So we've already gone through this right here. Not going to do that again. How did I get in? Oh, I don't know. I want to go to number 2 right quick, just to see if you caught what we just did. I'll give you 2 minutes, 1 minute on each to draw the enol form of the product, not the keto form, the enol form. Enol form. All right, again, that's gonna depend on the regiochemistry. And in order to predict the regiochemistry, you gotta know what reagents you're working with. If you're working with BH3 and hydrogen peroxide, the regiochemistry is anti-markovnikov. If you're working with mercury sulfate, the regiochemistry is markovnikov. And again, in both cases, you're adding H and OH. Now, in the product, the enol, one of those pi bonds is gonna be missing now, so don't draw that, don't keep that triple bond in the product. And I wrote the carbons out here too, to make it a little bit more clear. All right, got a minute and a half. Really miss having a full classroom for people scrambling. I think the flip method with the videos first is much more effective when people actually come and have to talk and write. You know what I'm saying? Yeah, it's much more effective. Yeah. And it's less talking to you, because you come in and you just work through problems. Anybody got the first one yet? We got 20 people in the participants box. I know one of the 20 has to have it. At least one now. I know it might be more than one, but at least one has to have it. All right, first. So there's a double bond, right? You know that. Not a triple bond anymore. What's the regiochemistry for hydroboration? And thermocarbon. What does that mean for where the OH is going? It's going to be here, right? I'm just going to abbreviate that part. I don't feel like writing all of it. All right, is that right? That's the enol form. What about for the other one? The mercury sulfate one. What about that one? What does the enol form look like for that? The same, but opposite. All right. The thing, here's another rule of thumb for your enol. If it's terminal, like the top one, it's going to turn into an aldehyde. If it's internal, like the second one, it's going to turn into a ketone. So this is a terminal enol. So when I write that as a keto form, I can just write this as an aldehyde. So the carbon, H, and we'll have another H on it. Because one of the H's came from that OH. And I'm just gonna abbreviate that part. And then the same thing here, since this is internal, it's gonna be a ketone. Now, I like the one that came from the OH. So terminal enol will give you an aldehyde, and internal will give you a ketone. Unless the alkyne is substituted on both sides of the carbon, then you're going to get a ketone regardless. Because you'll have carbons on both sides. All right. So you see how the OH is on the end carbon, and there's a hydrogen in there. So it's terminal. Terminal means the very end. Internal, the OH is on this inner carbon. Let me highlight that. When I say terminal carbon in the sense of a chain, a carbon chain, it's just the carbon at the end of that chain. All right, any questions about that? I know it's a lot on the first day of this section, but you're gonna have to try to get in the gym a little bit and do some push-ups from now until December the 5th. You gotta do a lot of push-ups. Not saying you haven't been already, because I think you guys study pretty much, study a lot. I can't say the same for other class, but this class, I know some of y'all are really on it, so. All right, if there are no questions, we gotta stop here. Because we only got 3 minutes left, and I don't want to start with the reaction wheel, but we're gonna finish that on Friday. And we're gonna draw all those products. And we're gonna talk about sequential reactions and all that stuff. So don't panic. It looks like a lot, but it's really not as bad as it looks. I actually wrote this question as a test question. I forget what year, but I had a group of young ladies who were all pledging Delta. And they weren't coming to class, so this was my sledgehammer question. And it worked. They started back coming to class. But anyway, we'll stop here if there are no questions. And we'll pick up on Friday. Y'all have a good Wednesday. And go ahead, Savannah.